Hey, welcome everyone to cloud computing. This is cloud computing and next door is data sharing and distributed processing, I believe. So today we have Naomi Alterman, who is the eScience Institute's technical education specialist and also our cloud guru. So she'll be telling you all about how to use the cloud. So take it away, Naomi.
Thank you, Noah. Hello, everybody. I'm going to be trying to make this an interactive session. I'm going to want to talk to you all a lot. So on the one hand, I want you to feel absolutely free to ask questions out loud. That goes for if you are in person or on this wonderful internet of ours. I also, because I'm going to have some prompts that I want you to respond to, want y'all to make sure that you are in the Alterman-Cloud Slack channel. So if you could all make sure that you join this Slack channel, hashtag Alterman-Cloud, and then react with my little eyes emoji on the slide deck post, just so that I know that everyone is in the Slack room and that when I ask for you to respond to my questions, you'll be able to throw your answers up quickly and easily. Oh man, wow, that went from 1 to 10 really quickly. Excellent. And that is the link to the slide deck I'll be using. That should be an evergreen link that will last for a while. So very briefly, a little bit about myself. I'm Naomi, as Noah mentioned. I'm a technical education specialist at the eScience Institute. And broadly, this can mean a few different things, but I think that most importantly, the way I describe what I do is that I'm a facilitator of information between complex domains, whether that is people learning how to use technology or software interacting with hardware or scientific experiments interacting with cloud systems. I like thinking about the ways that information gets serialized into a bunch of symbols, sent somewhere else, and then expanded back into meaning. And so today, we are going to be talking about how to use cloud computing. Specifically, we're going to be talking about what the abstractions for cloud computing is. This is going to be more of a philosophical tutorial than a hands-on tutorial, and I'll get to my motivations for that in a second. But we are going to talk a little bit about practicalities of if you wanted to get like your hands dirty working with cloud technology, what that actually means, the different ways that that can be what you're doing. There are a lot of different meanings of working in the cloud. And then we're going to talk a little bit about meta skills for how to use the cloud effectively. There is a lot of content in this slide deck, more than we will have time for. And so I hope that you find the content that comes after the ending slide in this useful, and I'm happy to answer questions about it either on Slack over the next few weeks or over email, which I hope you consider me a resource for you even after Neurohack Academy is done. But first, before we get any more into detail with all of this, I'm interested in what you all think the term cloud actually means. And so I don't want you to respond to the Slack channel just yet. I want you to type your response out and not hit enter. And there's always someone who doesn't follow that instruction and just hits enter immediately. And no shame, I get excited too. But type your answer out, don't hit enter, and wait until I say go. I'm going to do a countdown, and I want everyone to send their definition of cloud to the Slack channel all at once. So take a minute to write your message out, and then don't hit enter yet. Okay, take a minute to finish your definitions. I'm gonna say go in just a second. Finish out the sentences that you're typing. We're not looking for rigor or accuracy here. There is very little accuracy when it comes to talking about tech that involves buzzwords. Okay, 3, 2, 1, go. Yeah, okay, great, excellent. This is what I love to see. Servers, some in Iceland, question mark. Shared remote directory for storing data and information, some kind of ambiguous large server that stores data, can be accessed by many locally. Cluster space, online resource to manage data. Internet dependent space for data and processing, accessible regardless of physical location and device. The cloud is a buzzword for the collection of data and processing units networked through the internet. The cloud is a bunch of expensive CPUs and memory that you never have to upgrade, clean, or replace. The cloud is something that's not physically there, but somewhere out there forever. I like the ambiguity of some of these. Whoa, a smorgasbord of computation. Very good. Yeah, I think that these all access a lot of different parts of what the cloud means when we talk about the cloud. But fundamentally, whenever we say cloud, we're talking about doing computation using a service that is not based on machines that we can manually touch and manipulate. Maybe we can conceptually and hypothetically touch and manipulate them. But the idea is like, you know, you're doing some work on your laptop, you can close your laptop and go to a different computer in your lab or at home and begin working on that same content because the brains of all that stuff is stored somewhere else. Now, the way that that gets done, the way that that gets accomplished varies quite a bit. And so one of our goals for this session is to give all of us a shared language for what the fundamental building blocks of that cloud computation are, so that you'll have the agency to be able to talk about it and manage budgets that involve it and manage contracts and negotiate access rights to data that involve this. And this is really important because now more than ever, the cloud is beginning to become a thing that we have to deal with, whether it had previously been relevant or not. How many of you have heard about this headline about the UK Biobank restricting their data to only accessible on the cloud? Yeah, I found out about this because I ran into Ariel at a stoplight a few weeks ago, and he mentioned that the field was getting spicy because this is happening. So I went and I read about it, and I was like, oh man, this is the story, regardless of what scientific field you're in. We're at this point in the history of science using computation, where we are beginning to see a shift from resources that we directly manage and purchase to resources that we are renting on our behalf, but in the server farms of a large computational center, whether that is a private computational center managed by a for-profit company like Amazon or Microsoft Cloud, or whether that's a national resource, like a national cloud funded by the NSF. And this, I think, is part of a larger sort of trend that looks sort of like a pendulum in terms of where we're doing our computation. So early on in the history of computers, you would not have had a computer on your lap. You would have had something that looks a lot like a computer, but this thing fundamentally was kind of like a Chromebook. It wasn't doing anything other than sending your keystrokes to this thing, and then taking the output of that thing and putting it back on this CRT monitor. And this is a little bit inaccurate because this is not an early computer. This is a relatively recent computer in terms of powerful computers. So I thought it looked cool and like the movie Tron, so I chose that one. So, you know, through the 90s, this would have been a very common pattern where the amount of computational power that you could properly buy and keep under your desk was not ultimately enough to be doing interesting science. And so what you would do is rent time on one of these supercomputers, or maybe rent time on a supercomputer at a different organization, which is why we invented the internet, and send instructions to it through a terminal, through a thin client, through a little keyboard and monitor that connected to the thing that was actually doing the computation. Then, towards the end of the 90s, in the 2000s, we suddenly began experiencing this whole thing where computers were becoming rapidly more powerful, and you could do, you can't do things that, this is a really bad choice of image, because that is a very powerful computer, but you could do very interesting things with one of these computer towers, and you can get your lab to buy 5 or 6 and keep them in the storage closet. And now you have all the computation you need to do your science. And it's a completely reasonable way to manage a laboratory budget. But then we begin seeing, well, you do quickly outgrow those machines. And something that we realize is that it's a pain in the butt to manage these machines because hard drives die and CDs get scratched and power goes out. And sometimes if you're in a bad building, then the rain trickles in through the ceiling and then like floods the floor and like shocks the computer, and then you have to open it up and scrape all of the corrosion out with a screwdriver and get one of your coworkers to bring a beach umbrella and put it up on top of the server so that the water streams around it instead of on top of it. I'm not joking. I worked at a startup once where that was the solution to our server closet. This is why people don't want to manage their own computers, why you want an IT person to manage them for you, and you want that IT person to have the budget and latitude to do it right, as opposed to putting the machines in a closet and putting a beach umbrella on top of the machines. And so that's why we see a movement from these personal computers back to central IT, where you have the IT department of your university managing your machines that you still buy, but you put them in a data center managed by the university and then access them remotely again, just like we did in the 60s and 70s and 80s. It's just now we're using Jupyter Lab and it's in Google Chrome and it looks a lot nicer than the VT100 terminals, but it's not really that different of a thing. The key here, though, is that we still are buying that hardware and ultimately we still have to sell it when we're done with it or junk it. So what we're doing is making purchases of machinery, using them for some number of years, amortizing that cost over the initial purchase and saying, well, this costs like $10,000, but I'm going to use it for 5 years. So like I'm terrible at mental math and I'm not going to divide 10,000 by 5, but like seems more reasonable than it would otherwise. Is that 2,000? Okay. Yeah. So we've reached this point where we have a lot of purchased computation that our lab can use. And it's also gotten to this point where universities that are well endowed might be buying lots of computation for departments to use, like by chipping in through indirect costs and things on NSF grants. And it gives the appearance that there is a lot of free or cheap computational power that is all possessed locally by the university. What we're beginning to see is that the amount of computation we need to do the kinds of science we want is beginning to stretch thin the amount of computational infrastructure that a local IT department wants to invest in and wants to manage and wants to maintain. There are plenty of universities and institutions that don't have the budget to buy these things and maintain them and then surplus them and sell them when they're done. And no matter what, if you're a neuroscience researcher, you probably don't want to be worrying about these racks at all. You want to be thinking about, the little strange attractors and stuff that you're studying. So thus we begin seeing this shift away from computers managed by your institution and towards computers managed by someone else. In this graphic, I have the 3 big tech company clouds, so Google and Amazon and Microsoft. But in the case of UK Biobank, they are providing their cloud platform. I believe secretly, or not secretly, I think it's actually on top of AWS, But this is why it's tricky to talk about the cloud in a context that's applied like this. If this were a room full of IT people, I'd be like, let's talk about network adapters all day. But for you guys, what's relevant is the fact that we can do things with this computation. And this computation is ultimately managed by Amazon. UK Biobank is figuring out how to provide a platform to you that you don't have to think about Amazon or the fact that they have a cloud. You just have a login and a billing code, and you pay UK Biobank to have compute time in their cloud, which presents you a little Python window. And that goes towards their budget, which they use to pay Amazon, which they use to rent time on Amazon's computers to run your Python code. And so cloud computing ends up meaning all of these things. And depending on your job and depending on your responsibilities, you do or don't have to worry about some collection of them. And so at this point, we're going to spend the rest of today talking about what the building blocks of these cloud platforms are, so that you'll be able to have informed conversations with people like UK Biobank and like the people who manage these big data sets that they want you to access through their cloud services. But before I tell you all these things, I'm interested in having you tell me some things. So I have another couple of prompts here. I'm interested in your take on what the pros are of paying someone else to manage your computers for you and what the cons are. What are the pros and cons of having the hardware you deal with and the compute platform managed by someone else? You solve a bunch of problems with dealing with hard drives crashing by giving someone money. I want you to brainstorm different ways that there are pros and cons and post them to Slack. You don't have to wait until I say 3, 2, 1, but you do have to give me a lot of them. I'm not actually going to move on until you give me enough pros and cons that I'm satisfied. And I'm going to be very awkward and just sit here in silence and go like more. So, start sending them to me to get past this horrible, awkward part. Some good ones already. You don't have to know how to manage computers. You don't have to think about it, but you do have blind trust in their ability to do it right. Unpredictable when they need to clean up a cluster. Always when you need to run analyses, no doubt. Cons, money. Cons, less control. I appreciate this one a lot. Pros, no headaches. Cons, headaches. Yes. Very true. Part of the promise of the cloud is that, we take care of all these things for you. And all you need to do in order to have us take care of these things for you is read an 800-page book and take a certification course in how to use our platform. All right, you don't have to wait for someone to fix things for you. Oh, you have to wait for someone to fix things for you. That's a con. I would also offer it as a pro. There's a pro that if a hard drive crashes, there is someone on call at Amazon who is going to be fixing that within like a quarter of an hour, as opposed to waiting for your IT person to be woken up and get to the lab in the middle of the night. But the con, of course, then is, when your own things on the cloud break, then it is sort of your responsibility to figure out why. Pros might be more secure than your systems, but the cons are it might be a bigger target for security threats. Yeah, this is one of the reasons that I saw UK Biobank post that they were going to force things to be cloud only, is that it gave them a more uniform way of managing access to a bunch of potentially really highly sensitive private biometric data. Seeing a lot about security, seeing a lot of cons about customizability or control. Oh, this is a good con. Worrying about budget continuously versus the upfront cost of just paying for a local computer. Cons, need to wait in line if too many users are accessing at the same time. I both validate this for dealing with like something like a GPU, which the cloud may have a shortage of, but also pro in that if you hit that resource contention at your home institution, then you always have the ability to check if it's available online on the cloud. And I'd also offer that there are many different regions in the world that these clouds are based. And so depending on, which cloud you're going with, you might be able to check, well, it's peak time in the Pacific time zone, so all of the GPUs here are in use. But if I look at Central Asia, then it's the middle of the night and there are a bunch of GPUs that are available for me to use. And I just have to tolerate longer latency time, which for scientific workloads is usually okay. These are all very good. Thank you, everybody. Oh, and you've kept going. This is so great. Con, an update can ruin your processing. Yeah, you have to, this is part of that theme of control. You need to know what they are doing and you need to be able to react to it when someone else manages your software and your system. Pros, you don't have to wait for your PI to retire an old computer long after it's due. Yeah, that's actually like a big thing that we see in cloud computing right now, is that GPUs are changing a lot. And rather than buying like a bank of 10 GPUs and then being stuck with them for 5 to 10 years, people are saying like, look, I just want to rent whatever is currently top of the line. It's going to cost some money. I'll build it into my budget when I put together my NSF proposal. And then I get whatever is fresh and new. It's like constantly leasing a car instead of buying a car. But buying a car can be nice. Then you don't have to feel bad if you spill your Starbucks Frappuccino all over the seat because you're very excited about cloud computing and it's 7 a.m. on a Tuesday morning. Pros, computing power. I accidentally went to my next prompt. Okay, well, so I am satisfied. Thank you all for thinking about the pros and cons here. I think that ultimately what I wanted to get across here is that this is not necessarily a final decision that you have to make. Am I going to be a cloud-based researcher or not? This is a constant question about the options that you have to do the computation you need. So there are major benefits to using the cloud in many cases. There are major benefits to using local computation, by which I mean not just the computer on your lap, but also the computers your university might have, if they are available to you and if they're more cost effective than what the cloud is presently renting out. I know that one common thing that gets done at university IT departments is the ability to burst from local resources onto the cloud when resources here are in contention, and just have your workload very easily have the ability to begin using cloud computers instead of local computers. This is also sort of a constantly sought after, constantly developed solution to dealing with the pros and cons between cloud computing and local computing. In the case of UK Biobank, though, it's tricky because that's I think 30 petabytes of data. And that's the kind of thing that's just not practical to download that easily, at least not in its entirety. We also see an issue where several different universities might want to be collaborating on a data set that big, and it might not make sense to make a copy of that data set several times. I was also looking at the UK Biobank's justification for what they were doing, and it was really interesting to me to see that they were talking about when you finish your work with their data, they want you to return your results to them, which is to say they're very interested in taking the secondary products of what people create using this data and then bring it back into their data resource so that other researchers can use it as well. So this, I think, really sort of braids these conversations of collaboration and open science and accessibility of compute resources into this very technical conversation about where are the computers located and who's updating them, and do we have to worry about power stuff and cooling stuff. It's tricky. Just to get a little bit more philosophical right before we get super concrete, I have one more prompt for all of you. This is a 3-2-1 prompt, so I want you to think about this and then hit enter when I tell you to. How might renting compute instead of buying it change the way you ask scientific questions? So what I'm interested in is, if you have to think about paying for compute per hour rather than buying a computer and using it for 10 years, how does this affect your scientific process? I think depending on your disposition and your previous experience, this could be a very negative sounding thing, but I don't intend for it to be. I think that this can facilitate things. It can also create major drawbacks. And at this point where certain data sets are becoming only available on the cloud, I'd like for us to be cognizant and think about how this changes what we do independently of cloud computing. So think about that, and then I'm gonna shut up and then ask you to hit enter in a minute or two. I'll take a minute, finish writing your sentences. I'm gonna say go in a minute or two. All right, go. Lots of good ones here. It depends on the cost. I feel like I'd either get a project done a lot faster or a lot slower, depending on the rental cost. You may be pressured to finish earlier to save money. Well, and it's easy to waste a lot of money and get an angry PI. So you might be asking simpler questions that you know you have the analytical skills to conduct. So I'm seeing a lot of like being careful about what you set off to begin asking. Less time spent on exploration and hypothesis generation work, more focused hypothesis testing. But I'm also saying that this could expand the scope for short-term projects with large computing needs because you only need to pay for the time that you use the resources. This is a really good point. I think that especially for earlier stage researchers where you have ideas about things you want to explore, it might be hard to justify the cost of buying compute, or maybe the compute that is available to you at the university is already in use. Or maybe you're at a less well-funded university and you don't have compute that you can use. Ooh, the lit review, the brainstorming, and the planning phase would be a lot longer. Maybe you would run more pilot work to ensure that you're asking the right scientific questions and not wasting time on things that don't work. I find that I appreciate the words of that last sentence. Not wasting time on things that don't work. For different definitions to me of wasting and value and different definitions of work. You could be constrained or could benefit by the data resources you're allotted, and what you can afford and what you have access to. These are amazing, guys. Thank you. If you're renting for a specific time, then time efficiency becomes very important. Whoa, you might be able to ask questions that require more data or compute than would previously have been possible at scale in your lab without cloud computing. Yeah, so we're seeing a lot of changes in how we go about our scientific process because of the way that compute is beginning to become available to people at scale. It's a very interesting time to be paying attention from a meta scientific level. And I encourage you, as you see headlines about these things and you begin being faced with questions about whether you want to be doing something on the cloud or not, to be thinking about these sorts of things in addition to your line item budgets. Because I think that what we're seeing here is a very subtle difference in how we do our research, the same way that the presentation of computers themselves produces a subtle difference in the way we do our research. I mean, maybe you challenge me on saying it's not subtle to use a computer versus not, but I would say that there is probably a subtle difference in the types of questions we formulate now that we know there are computers that we can use to crunch numbers. There are probably different questions we're going to be formulating now that we are thinking about computers in terms of renting them by the hour rather than having them under our desk. So enough of that philosophy. Let's talk a little bit about building blocks. So when I talk about building blocks here, I'm saying this because I want to get on the same page with everyone about what I mean by the cloud and what ultimately the cloud is, regardless of how many intermediaries you are purchasing it through. So if we talk about a consumer cloud product that is not based on computation, some people refer to the cloud as Google Drive, where you have Google Docs for Word documents and you have spreadsheets for Google Sheets. This slide deck is hosted in Google Drive using Google Slides. In this case, the building blocks are these types of documents. We can create a shared presentation on this cloud platform. We can create a shared spreadsheet, and it's hosted somewhere that if I turn this computer off and open another one, I have access to those things. And so in terms of the cloud that you're using for this Neurohack Academy, I would put forward the building blocks are Python notebooks, but also the Python console itself. Like you can just type Python commands in or run Python scripts. And also terminals. If you want to do something that does not involve Python or that involves special Unix commands, you can open up a terminal in addition to your notebooks and in addition to the other things. And so the thing that I wonder is what the equivalent building blocks are for an infrastructural cloud service, or maybe we can think of this as an IT cloud service. Because what that is providing us, what Google Drive is providing us as a cloud, is it's a personal cloud, it's a data cloud, it's a office cloud. What Jupyter Hub is providing us, Jupyter Hub as a cloud that we've created for this event, it's providing us programming opportunities, it's notebooks and things. So what is the IT equivalent of these things? So there are two main ones, and the most important one is probably no surprise, computation. The thing that you give Python code, or you give it C code, or you give it whatever, and it follows the instructions in the code you give it, it takes data, turns it into other data. In Cloudland, we call these virtual machines because they're very analogous to the machines that you have on your desk in front of you, or that are in the server rack that are in the basement of the building you work in. On AWS, on Amazon's cloud, their brand name for virtual machines is EC2, which stands for Elastic Cloud Computing. Yeah. On Azure, they just call them virtual machines. I think on Google's cloud, they also call them virtual machines. I should be embarrassed that I don't have Google's brand names for things on these slides, given that this is a recorded presentation. But it's also like the third year running I've not had Google's brand name on things. So Google just knows I don't like them at this point. The other, I'm joking, by the way. I think Google's a perfectly good platform. The other common building block here that we're going to think about and that you see show up a lot, whether you're using Google Drive or Jupyter Lab or these IT systems, is cloud storage. How are the data sets that you're working with kept in the cloud, and how are you being charged for them? This is a place that gets less and less analogous to the machines that are on our desks. So there are many different types of cloud storage. There are different ways of storing data in one of these IT clouds. And so the most common one, or not the most common, the one that's most familiar to us would be called file stores, which is similar to the way your Google Drive is organized. There are folders with files in them, and you can delete files and move files around. There's also something called object storage, and we're going to get into detail about what object storage is in just a moment. But this is a more cost-effective way of storing data. There are lots of branch names for these things on AWS, that is Amazon's cloud. It's called block storage and elastic file storage, and S3, which is their object storage system. It's called simple So I don't know what S3 stands for. Azure, they call these file stores and blob containers. I think Google Cloud calls them file stores and object storage. Google tends to be low brand name. AWS tends to be very high acronym. Azure tends to be like cute brand name, like blobs.
Simple storage service.
Simple storage service. Thank you, Noah. Also, I guess Amazon's also tries to get cute sometimes because they have Elastic Beanstalk as one of their offerings and like Fargate and all these things. There are a bunch of other abstractions that are really relevant if you're trying to say, set up a Jupyter Hub. They are less relevant if you are a user of a Jupyter Hub, even a paying user who's like paying UK Biobank or maybe paying for the Neurohack Academy one by attending Neurohack Academy, and so the registration helps cover that. But regardless, there are these building blocks that we think about a lot when we build platforms for other people to use using cloud IT. So we talk a lot about networking, that is how these things are connected together and how they're ultimately connected to the internet and all our laptops. We talk about blank as a service. This is kind of the abstract one, but the cloud providers try to offer a lot of value add services where if you had to run a database server, you might not want to worry about whether there are security updates for that database server or whether you are running out of disk space for that database server. You just want to pay more for the disk space and have it magically appear. And so the cloud might provide a database as a service. And whenever you see this blank as a service pattern of words, what they mean is they're going to take something that you would normally be setting up on a computer yourself, like by installing software and writing configuration files. And they're doing that part for you so that you can just sort of log into it and get started using it. You could look at like our Jupyter Hub here as like a Jupyter Hub as a service. So presumably we as Neurohack Academy did not have to set up the Jupyter Hub and install it and everything. We paid someone to do that for us for some fee structure. There's also this notion of users and security. It almost always goes by the term IAM, Identity Access Management. And this is the very powerful and nuanced ways in which these cloud platforms decide who has the rights to create and delete virtual machines, who has the rights to create and delete storage containers, who has the rights to look at the storage in the first place. If you think about the cloud resources on this slide as like physical objects, IAM is really concerned with who has the physical keys to the server room. And this doesn't necessarily involve, my brain just got to say. This IAM is not necessarily concerning who logs into the resources you create. So we created a Jupyter Hub. IAM is not concerned with whether you're allowed to log into the Jupyter Hub or not. IAM is concerned with whether you're allowed to delete or create new machines that are serving the Jupyter Hub. These are really keys to the server closet. And then the last building block that I think is really valuable to mention, even if you don't end up touching it yourself, is location, which is to say the literal physical location on the planet that all of the physical machines that back these things is located. Cloud platforms, when you're building stuff at this level, give you a lot of control over which region you place your computers and your storage in. And this can really make a big difference. Say if your data is all located on servers in the United Kingdom, you want to locate your virtual machines in that same region so that you don't have to worry about getting the data through undersea cables all the way to machines that are in Ohio. If your data is in Ohio, then even if you're in Washington, you want to put your machines in Ohio. Because fundamentally, it doesn't really matter how long the cable is. If data has to leave the physical building, then it's much more costly than if it stays within the same physical building. And so that's the level of granularity that they have us thinking about when we talk about regions in cloud computing. They're really talking about a data center that is very highly networked within it and highly bottlenecked when you have to go outside of it, even if it's still within Amazon's cloud. So you usually do not have to think about things in terms of creating a new virtual machine or setting up the IAM configuration for your storage. If you are, say, logging into this Jupyter Hub or logging into UK Biobank's resources, which as far as I can tell is presented as a Jupyter Hub. It's quite a common interface to use cloud computing. But these details leak through. These have ways of showing up even when we don't like do a lot of information technology management ourselves. And so we're going to drill down a little bit into these two most common ones so that you'll be able to talk about them with the people who manage the Jupyter hubs that you use. And if you are in a position to begin creating your own cloud computation platforms for work that you do in the future, then you'll have a little bit of understanding of how to read the pages of documentation that these cloud platforms throw at you. So let's get started and talk about virtual machines. In terms of machines, there are two aspects of them that we want to think about, and these are very analogous to the hardware of a computer and the software of a computer. So when we talk about the instance type of a virtual machine, what we're referring to is really the equivalent of what computer processor is on the motherboard of this thing. We're talking about how much RAM is in it, how many gigabytes of memory. We're talking about whether there's a graphics processor in there, which these days is almost never used for graphics and almost always used for machine learning. We talk about storage. I mentioned all of these different cloud storage options, but fundamentally there does end up being an analog of the hard drive that sits inside of this tower, or the hard drive that sits inside of your laptops. And you do get control over how big of a hard drive is installed in this thing. You usually don't get to change these knobs individually, like say like, oh, I want to take this VM and add 3 more gigabytes of RAM to it. Usually the way that this choice is presented to us is as pre-configured instance types. And so there will be a VM instance type that has 4 CPU threads and 16 gigs of memory. And it's in a series that all have 4 CPU threads, but maybe increasing amounts of memory. And each of those have a different price associated with them. Some of them end up being very costly. Some of them can be very, very cheap. And to give you a sense of the range that I'm talking about here, if we talk about an hourly charge, some of these VMs can cost a fraction of a cent per hour. And some of these VMs can cost $100 an hour. And the difference really just comes down to how much of these 4 things you need. In terms of the software on a computer, these behave much like any other computer that we interact with. So they have terminals that we can type things into. We install software on them. We have folders that have data and user configuration, all that stuff. But what comes preloaded when we first create a virtual machine and turn it on is what we call the image. This is sort of like the stock stuff that's on your MacBook when you first open it up. You can think like you have Apple Music on there, you have Apple Calendar, maybe you have a photo viewer, but you don't have Spotify. And so you need to go and download Spotify. The image is everything that's installed when you first turn the computer on. One of the cool things about the cloud is that we can make images out of a pre-existing VM that we've installed things on, and then we can use that image to create new VMs, sort of like a template that we stamp down multiple times. Or we could turn a computer off change the instance type and turn it back on. So it would be like if you closed your laptop and said, I would like this laptop to instantly be 10 times more muscular, but also 10 times more expensive. And I'm just gonna do that for like an hour while I do my computationally intensive work. Then I'll turn my laptop off, make it much cheaper to run and much less powerful. And I don't have to do any management of the operating system because that's all handled by the VM image. So when we think about virtual machines, we're really trying to think about two things at once. We're thinking about the instance type, the instance of the hardware that is somewhere out there in the world, and the image, what comes pre-installed on it. And so I want to emphasize, these are charged per hour of on time. One learning moment that I find a lot of researchers get when they come from high performance computing backgrounds is if you use supercomputers, then they'll often be charged by the percentage of CPU time you're using. So like if your computer goes idle, then you're not being charged as much as when you're really doing a lot of work. In the case of cloud computing, you are simply charged when the machine is on, and you are charged at an hour time scale. There are some exceptions to this, but it's almost always roughly at those scales. And so you turn your computer on, you do some stuff, and then you remember to turn it off because whether you're using it or not, it will accrue charges in your account. These are very easy to resize. That is to say, you can make them very powerful or very weak but cheap. They're very easy to duplicate, and something that I had to learn, which was tough because I'm a vegetarian and I don't like thinking about industrial farming of cattle, but we're encouraged to think about virtual machines as if they are cattle, not pets, which is to say that if you have a pet computer, then you give it a name, and you care about it if you drop it off a desk and it gets hurt. You want to make sure that it lasts you for a long time, so you invest in keeping it safe. You get like a nice case to carry it around in that's like a pretty color and has this diamond pattern on it. But for virtual machines in the cloud, we treat them like cattle. They're there to be used, and as soon as they stop being useful to us, or if they break because we misconfigured something, we turn it off, we delete it, and we create a new one. We have no emotional connection to them at all. And this might not be a hard thing to do if you're a person who doesn't care about your computers. If you are a huge nerd like me who personifies your machines despite trying as hard as you can not to, then it's a hard thing to get used to. That these are things that are very easy and cheap and good to delete at a moment's notice and create new ones. And if you want to know who taught me this phrase, it's that guy right there. It's hiding in plain view. That is my manager, Rob, who knows more about the cloud than I do. So you can bother him with questions as well. I'm sorry I called you out, Rob.
That's okay.
So drilling down more into VM sizing, that is the instance types that we're using here, there are a lot of different ones. If you are familiar with bicycle gears, forgive the tangent for a second. There are sets of gears in a bike, and so like if you change your major gear to 1, then there are these minor variations of like minor gear 1 through 16, and then major gear 2, minor gears 1 through 16. And they sort of like overlap, like gears, all the gears in the 1 set are relatively small. And then all the gears in the 2 set are a little bigger, but they overlap with the other set. So like the most powerful 1 gear is still more powerful than the least powerful 2 gear, but like less powerful than the most powerful 2 gear. I used to have a diagram showing that on this page. I'm realizing that if you're a visual thinker, it's hard to talk about this without that. What I mean to say though, is that you see a bunch of different instance types with wildly different configurations and wildly different prices. And the real skill here is figuring out what series to care about, because within an instance series, there are going to be many different machine types of different sizes that all have roughly the same skills that they're good at. So this is an unsorted table of instance types, and there's no rhyme or reason to like you know, why something is in this table or not. It's hard to compare things. But if we looked at the documentation for each of the major cloud providers, we'd see that those letters at the beginning of the instance name indicate that they are part of a series that is very good at specific things. So maybe you don't need a lot of RAM. You can get by with 2 GB of RAM, but you need a lot of CPU cores that are crunching numbers in parallel, all at the same time. Then we care about a compute-centric virtual machine. Gotta get my cursor over here. Maybe you care a lot about a lot of RAM. You have a big data set, a big matrix that will only fit in 128 GB of RAM. And you're just going to be taking your time going through that matrix. And so you don't need to have a bunch of different CPU cores running in parallel. You want a memory-centric virtual machine type. Maybe you care a lot about GPUs. By default, most of these VMs will not contain GPUs because those take a lot of power and are quite expensive to buy. So those are sort of premium virtual machines. Maybe you don't know or care about any of this and you just want a generic series. And so it pays off to read a little bit on the cloud platform that you're going to be using to see what their different virtual machine series are, because this is the level of information that's really useful. If we talk about this gets overwhelming real fast. But if you figure out, oh, okay, I need the Z series of virtual machine, then you can filter it to just be the Z series because you know that you need whatever it is the Z series is good at. And then you see your price options for the Z series. The really cheap ones that have only a little bit of what you need, the really expensive ones that have a lot of what you need. And if you ultimately don't care and just want to be told what to use, on AWS, if you're creating a VM, make a T3 large. On Azure, make a D2, D5, and on GCP, make an N2 standard 2. And these all cost you about $2 to $3 to run if you leave them on 24/7. And I believe, I forget, these are all relatively equal amounts of power across each cloud platform. I think that the benchmark I used for this was like 4 CPU cores and like 16 gigs of RAM, probably feels like what I was thinking when I put this slide together last year. Though I mean, it's very easy to look at this thing and go, well, I tried creating a T3 large and my work kept freezing up. My Jupyter Hub kept saying lost connection to host. And what that means on the cloud is that your computer is too small, so you just turn it off, make it one larger, turn it back on, and see if the problem is still there. And that's one of the nice things here. That's one of the big pros about renting your compute rather than buying it up front, is if you make an incorrect estimation, then you're not stuck with any more than 1 hour of money sunk into something. This can be really useful for speccing out how much compute your workload needs, even if you're gonna buy it in the future. And so this is why I think that it's useful to play with this stuff, even if you mostly use on-premise computing, because this is a good prototyping tool. When we prototype things, when we don't know what we're doing and we're just exploring, then it can be really helpful to make decisions that don't have big costs associated with them. And so in this case, there's a big cost associated with doing data exploration because we're being charged per hour. But if we know the type of data we're exploring, then there's a relatively little cost for exploring the hardware that we need to do our science. Agency, trade-offs. These provide a very different type of experience, financially and in terms of the user experience, than buying computers up front. And this choice continues onto storage as well. When we talk about storage, I alluded to the analog of the hard drive that's physically in your computer. On the cloud, this is called block storage. And so block storage across the cloud providers refers to the hard drive that's in the virtual machine connected to the motherboard. These are the fastest type of hardware, and this can make a big difference in the computation you're doing. This can make the difference between like 30 seconds of computation versus 7 hours of computation. Usually, in terms of size here, we're talking like 4 gigs to 512 gigs. And I would personally consider 512 gigs to be quite a lot of block storage, because that's a really expensive way to reserve space on the cloud. If you think about it in terms of ways that the cloud provider can cut corners, you are reserving the whole hard drive, whether you're using it or not. Because at any given moment, your operating system could decide to use one of the sectors in it. So we generally end up seeing that this costs about 16 cents a gigabyte, which doesn't seem like that much money, but if you think about it at scale of like, well, my data set is 30 petabytes. You can like do the orders of magnitude multiplication here. Actually, this unit is incomplete. This is per gigabyte per month. So in a given month, your hard drives are costing you 0.16 times for the hard drive that's sitting in your virtual machine, whether you're using the VM or not. So you're charged for the CPUs and the RAM in the VM per hour, but you're charged for the block storage per month. On Amazon, this is called EBS, Elastic Block Storage. On Azure, this is just called disk storage. I think on Google Cloud Platform, it's also called block storage. So the next step up from this is file storage. This is more flexible. You can think of this as being much more close to Google Drive or Dropbox. It is a folder that you can mount on your virtual computer or on your personal computer that stores data in the cloud. It's much slower than block storage. And when I say much slower, it won't be visibly slower to you as a human being at human scales, but if your code has to access data in a really quick fashion, then you're going to begin seeing a performance difference between these two. But it's an order of magnitude cheaper. It's 6 cents per gigabyte instead of 16 cents per gigabyte. Is that an order of magnitude, or is that just a little ish? We're gonna get there though. On Amazon, this is called Elastic File Store. On Azure, it's just called File Store. On Google, it's probably called File Store. Now here's where we get more weird and more cloudy. Is object storage. When UK Biobank said that they were hosting their data only in the cloud, what they meant, and the reason why they did that, is because rather than providing data sets as file storage, as a folder that you can open up and get files out of, they're providing their data sets as object storage, which is the most cost-effective way to store files in the cloud. And generally, is interacted with programmatically. And I'll have a diagram showing what I mean by this in a second. But the idea here is that with a file store, any computer program that works with files can work with files that are in a cloud file store. With object storage, there's going to be a specific Python package that you have to install that lets your Python code do things with files from Amazon's S3 object storage. And you can still do whatever you want with that data. But if your code is not written specifically to work with data from S3, which is to say, if your code is not written to open files from S3, that's sort of where the interface shows up. It's like if you're reading a data frame into pandas, or if you're like using the Python open function, then we begin caring about writing special code. That's where things begin getting special, bespoke. That's where things become different. And this is worth the trouble because this begins getting an order of magnitude cheaper to store. We're talking 1 cent a gigabyte instead of 16 cents a gigabyte. There are a lot of trade-offs that come with object storage. They, as a technology, can be very flexible with regards to the performance that you get for storing data in object storage versus storing it in block storage. But ultimately, the idea here is that a lot of large data sets are moving to be stored in object storage because they let you play a lot of tricks with how efficiently things are stored and get a lot of cost savings from choosing to store things more efficiently. To make that more concrete, as an example, if you use a file a lot, then it costs more to be saved in object storage. Whereas if you haven't touched a file in 6 months, then it can sink into cold storage where it will take much longer to access, like on the order of seconds instead of instantly. But it'll cost even cheaper than a cent per gigabyte. That's why people care about playing these games. That's why UK Biobank said, you know what? We're gonna keep our 30 petabytes just in Amazon's cloud. And if you want to work with them, then you have to work with them in the same data center that all this object storage is in. Because it's gonna cost us a lot of money to let you access this stuff as file storage, or to let you take these objects out of the data center. Because we generally see that the way that cloud providers meter the data that goes in and out of them is that it's free to put data in a data center, and it costs some small amount of money to get data out of the data center. Rob, do you remember a figure that's how many cents per gigabyte? 10 cents, about 10 cents a gigabyte to download. So if you were to download, 30 gigabytes of data, then I don't know why I keep getting myself into trouble and posing mental math related things. It's 10 times 30. You could figure it out. I build computers so I don't have to do these things in my head. The motivations behind all of these moving into the cloud or out of the cloud all become based on what happens to be cheap and what happens to be technically difficult at any point in time. Because of Jupyter and because of our ability to write code that's portable and easily moved from one place to another, it's become more and more practical to take the work we've written on our laptops and have a computer in a data center run it that is next to physically a bunch of object storage. And so we're beginning to make decisions about, well, we can get a lot of things from that. We can make sure that all of the computers running that code are compliant with certain security and privacy regimes. We can make sure that those computers are always kept up to date so that they aren't hackable. These computers now cost money, so you have to pay for them up front, and because of that, that changes the types of questions that you're asking. But it also makes it practical to provide a data set of this scale to people at many institutions around the world, rather than being caught as the data set creator with the bill to transport the data out of the cloud and into everyone's computers all across the world through all those undersea cables. And so this is the trade-off that we keep seeing with these things. So this is just a diagram, what I was just talking about. Let's say that we have a data set that we care about and the data is all sitting in object storage in the cloud somewhere. We want to run our code on a computer that's also sitting in that same data center. And so we're going to do that by running Jupyter Hub, which is a server application on that virtual machine. And we're going to open a web browser on our laptop, which connects to the Jupyter Hub, which runs our Python code, which loads data out of object storage. When I keep saying load data out of object storage, the common way that that might look is if you have your full data set, that in your Python code, you download the files of interest that you're interested in. The files of interest that you're interested in. It's the end of the day. You download the parts of the 30 petabyte data set that you want to do analysis on. Maybe just some of the files you want to do analysis on. You run your Python code in order to do that work, and then you get output from your Python code. And so you upload the results of all of that work back to object storage, and then delete the temporary copies from your computer's hard drive. This is what it looks like whether you're doing things on your laptop or whether you're doing things on a virtual machine in the cloud. Secretly, when you use Python or when you use Amazon's Python libraries to work with S3, this is what's going on under the hood, no matter what. You're getting a temporary copy of just the part of the data that you're looking at in a given moment. You're working with it, and then it gets wiped away. And this is the trade-off for using object storage. Oftentimes, you have to be very cognizant. You have to be doing a lot of upfront thought about what parts of the data set you want to look at. If you're creating a data set, you need to be very cognizant about the chunks that the data set is cut into that allow people to download it. Because you don't want to force people to download hundreds of gigabytes of stuff they don't care about, just to get one small slice that they do care about. So you have to do a lot of thought about how do people access my data? How can they easily pick out individual pieces that they care about? Am I going too far in the direction of people picking out the individual pieces they want? And I end up with like a bunch of really tiny files, which ends up costing me more. There are a lot of trade-offs here. And so a lot of work has been done and is being done in any given scientific discipline, figuring out how to best store your data in object storage so that it is cheap for you to store and cheap for people to access and effective for people to do science with. You can probably publish a lot of papers about just finding a data set that you use and then figuring out how to optimally store it in object storage. Because people care about this. This means more science can be done if you can improve the cost efficiency of storing data in the cloud. And I should also mention that object storage systems don't have to be hosted in the cloud. The UW offers an object storage system called Lolo. Most universities offer some form of object storage in one form or another. So this is an increasingly common paradigm of how we take a big data set and we keep it somewhere that other people can access. And the last workflow that I'll mention is if you want to be doing computation, but you're not going to physically have your laptop open. There are a lot of different computational packages that let you take one Python program or one computational job and distribute it to many computers. And so Dask is an example of one of these pieces of software that let you do a computation spread over multiple virtual machines that you don't have to personally manage. Dask figures out which of these machines in this cluster are free, and it distributes your work to them. Maybe if you have GPUs, then the system that you're using also will like farm out the work you're doing to these different GPUs. And then you can turn your computer off and come back a few hours later. This is a really common workflow for people who are doing work that involves, say, training a machine learning model that's going to take 16 hours. And you want the thing to be done when it's done. You don't want to have to sit there and keep your computer on. And you also want these machines to be freed up so that you don't have to pay for them as soon as your machine learning job is finished running. Another term we might see for that kind of thing is a batch job system, which is analogous to the high performance computing batch job systems that you see in scientific computing. If the term Slurm is familiar to you, then it will show up in documentation for cloud clusters as well. A lot of the same technology we've used to manage on-campus computing is migrating into the cloud or has a version of it available in the cloud, so that we can move our work there as well. And so that's all of the concrete nitty-gritty that I have about computers. I have concrete nitty-gritty about bureaucracy and hierarchical structures, which I think is very, very useful. But before I get to all that, I want to pause and see if people have any questions, either online or also in the room, because we've talked about a lot of stuff. Even when I was asking you questions, I was asking you very specific focused questions. I'm not asking you meta questions about your questions. So asking questions. No, someone has a question. I can stand here until someone asks me a question. Can't whistle, but whistling would make it less awkward, so it's even better for me to stand in total silence. I see you, Megan. I know
I
we
just ask it. It's too long to type it out.
Good, ask it, yeah.
So basically, my question is, cloud computing. I'm understanding more from your talk, but I'm thinking in the context of like a campus visit for a job. How do I ask about their cloud computing in a way that I'm going to get an answer that I can understand? Like in order to understand what exactly their capabilities are.
Yeah, could you clarify a little bit about, so like, who are you in, or what, are you visiting a
What job?
campus? So like, as like, I'm going to work here and I want to know what they have?
Yeah, like
Or,
going on the faculty job market, understanding what kind of things they can offer me if I come there.
yeah, great question. So there are a few different dimensions to that, and I'd say the first one that I would want to address, and also thank you, by the way, for asking a question and asking a really good question, is financially, oftentimes there are a lot of different strings attached to cloud spend. So one example is the money that you have to spend when you download data out of the cloud. Some institutions have a waiver in place with the cloud provider to waive the fees for downloading data out of the cloud. The University of Washington is an example of one of those institutions that has a legal agreement in place with some of the cloud providers we use to waive fees for downloading. And so that influences the types of stuff you have to put into your budget and can really help. Institutions are also often able to negotiate contracts that change the prices of virtual machines. So one thing you can ask when you're on a job search and you're going to an institution is, what kinds of institutional contracts do you have with major cloud providers? A reasonable but problematic answer is none. You have to figure that out for yourself, which means that you are taking your budget number from an NSF award or from your credit card and using that to create your own cloud account. And that is easier than going through the institutional apparatus, if there is one, but that means you don't get the benefits such as all of these like fee waivers or negotiated prices. So asking if they have contracts with any major cloud providers and what the terms of those contracts are. Another good thing to figure out is how indirect costs play into the money that you want to spend on cloud. Are there waivers for if you get funding from a funding source and part of that goes to cloud computing? Does that money ultimately have some taken out of it to go towards the university as a whole? I think that's very commonly the case, but it's worth asking about because there are some institutions that treat these things separately and say, no, your cloud infrastructure costs are not subject to indirect costs. Other good questions, I think, are just what IT's orientation towards the cloud is. I think in most cases, university IT departments are not going to want to volunteer to help you with cloud things, but it makes a difference whether they have relationships with cloud platforms or not. If they know about or have relationships with AWS or Azure. A good thing that you can think about when going into these sorts of job searches is what sort of startup packages are available, and is there any way that you can have cloud funding as a part of that startup package? Because that's very often a way to get resources that are useful to you, but also like cheaper to get than other forms of money. So like oftentimes when we talk about paying for cloud, we talk about it in terms of cloud credits, which are very close to real money, but it's also sort of not real money. It's like if you have $200 in credits on Azure, which you can get, I think, just by signing up for Azure with a .edu email address, like that's not actual money, but you can use it to do things that would have cost you 200 real dollars anyway. And so like, are there cloud credits as a part of your startup package, or can you negotiate for there to be cloud credits as a part of your startup package? Because then suddenly you don't have to pay for the $5,000 of compute that you would have had to otherwise, or buy computers that you would have had to otherwise. Those are good things to ask.
That's
Rob,
great.
do
Thank
you
you
have
so
any
much.
thoughts about that? No, okay. Yeah, great question. Other questions? You know, part of my motivation here is that there are like 3 years of this slide deck in archive on YouTube, and also you have access to the slide deck. So like you can see all this crap. Like you can look at this later. But like, do you have questions for me now based on the dump of information that I gave you before this? More questions? One more question? I don't want to make people feel like the bar is too high. Like you have to ask a good question. Yeah. Yeah. What are hidden fees and restrictions that you want to keep an eye out for when you're looking at terms and conditions here? This is a great thing to think about, especially when you begin getting into programs that offer cloud credits. These are usually the sorts of things that most visibly show up for high contention resources. So if you have cloud credits, or if you have a personal cloud account that's not like an enterprise tier cloud account, you may be lower in the priority line for modern high performance GPUs. And this may or may not be visible to you clearly when you try to create a VM with a NVIDIA A100 GPU in it. And it's just like, well, there are no VMs available. Why is that? Maybe there are no VMs available. Maybe your user tier just isn't granted any in the quota. And so like looking at resource quotas is a really useful thing to do once you have access to a cloud account, because they're usually not set in stone. They're usually the kind of thing you can talk to support about and negotiate if you like bang on trash can lids loud enough and like get some attention. We have to do this on a regular basis because ultimately research is a relatively small business slice of like the business that these cloud providers are doing. So there is very good reason for us to get access to things that we may not be prioritized to get access for. In terms of other terms and condition things, I think that one myth I want to dispel about security here is that the cloud is actually an incredibly secure place to keep your data. In so much as there are a lot of businesses that would get really pissed off and like annihilate Google into the ground with legal bombs over and over again if Google had a breach of security at one of their data centers. Most security breaches tend to be in terms of the software systems that you set up in the cloud. And so the idea with security ends up being if there are important regulations you need to abide by, or even if you just care about the security of your data or the privacy of your code, you're not losing that by having Google manage the machine for you. And Google is not looking at the data in your VM to train their machine learning models. Using a platform as a service might be a different kind of question. So like as an example of platform as a service, Microsoft Azure gives you access to OpenAI's GPT cognitive services through an API. And those will have their own terms like associated with like the privacy of that data. And those are terms and conditions that are really important to look at. So when you're using a platform as a service, look at the data privacy rights for that platform. But generally, the cloud providers have a very vested interest in like not looking at what you are doing with your content, and also providing you tools with keeping your content encrypted so they cannot access it. We generally think of, and I'm like a like cynical, paranoid person who like hates large corporations, and I like actually have a fair degree of trust with what they say about, you know, treating your data with integrity and not looking at it when you create virtual machines or if you have a database that you run on cloud services. Really good questions. Got 9 minutes left. I think I've let it be awkward and silent enough. So I have more stuff that I can show you, but I'm gonna like zip through it because it's not that interesting. In case you ever have to use Azure or AWS yourself instead of logging into a Jupyter Hub that someone has set up for you, here are some tips and signposts along the side of the road to help you get oriented. On Azure, there is this thing called an Active Directory, and usually there's one of those for an institution. Actually, I think this is out of date because they renamed it. It's not, I think it's called like an intra directory. ENTRA, does that sound familiar? Oh God, they always change these names. Anyway, there is a user directory that is institution-wide on Azure, and this is really nice because you can easily say like, give your collaborators at your institutions permission to turn your VMs on and off very easily because you're logging in with your UW net ID. Within the Active Directory that you did not need to set up yourself, you get a subscription, and this is like the debit card that pays for things. If you're creating this account on your own, it literally has a credit card number attached to it or a bank account attached to it. Within a subscription, there are resource groups, and you can think of a resource group as a very lightweight sort of box that you are putting all of this virtual hardware inside of, and you write your name on the box so that it's clear that these are Naomi's PCs in the corner of the lab room, and that no one should be turning these on or off other than Naomi. Or if they suddenly start using a lot of power and the power bill goes through the roof, then Naomi's the person to yell at about that. And so it's easy to create or delete resource groups. This is one of my favorite things about working with Azure is that Amazon and Google don't have quite as easy to use equivalents of resource groups that let you just group the machines you're creating and easily remember what they're there for. And then within a resource group, you create things that actually do computational work and the things that actually cost money as they're turned on. A resource group costs you nothing. You can create 300 resource groups and it's just going to be free indefinitely. But as soon as this machine is turned on, it starts accruing charges. Meanwhile, in Amazon land, the image looks a little bit different. So when you get a cloud account on Amazon's cloud, then what you get is called an account that has an account number and also a set of billing codes associated with it. So this is what you put your credit card into and ultimately controls who pays for these things. Within that account is a root user, which they really don't want you to use unless you have to. And the root user has permissions to do everything with the account. Create new machines, create new users, delete users, remove access to the account for other people. And then underneath the root user are normal users. There are also these things called roles, which counterintuitively to me are the same things, but for slightly different purposes. These are what we actually log in with. So if we log into AWS, initially we only have a root user to log in with. We immediately, the first thing we do is create an IAM user and then log in using that instead, which has fewer permissions. And IAM users can then interact with virtual machines, which like on Azure cost things when they're turned on. And so the idea here is that the root user creates less privileged users, and the less privileged users create and turn on and off and use virtual machines. And as a reminder about cloud permissions and stuff, you don't need an IAM user to log into this remote machine. You can log into this remote machine if it's running Jupyter Hub using a username and password. You can log into it with an SSH key. But to turn the machine on and off, you need an IAM user who is allowed into the virtual room that the machine is contained within. There also is the ability to have an organization-wide organization managing all of these things. In practice, the UW at least does not seem to have one that they want researchers to use. You can usually ignore the presence of these types of structures. And then completing our tour through all these administrative structures, if we talk about Google, Google Cloud has this thing called a project. And a project is where you put your credit card in and you say everything that happens within this project is for my lab. So like rather than creating a project for each like project your lab does, the project is really sort of at a payer level. Like if you have a credit card, then you have a Google Cloud project. Within that, we can create virtual machines. Those virtual machines cost money when they're turned on. And separately from this, we also can have billing accounts, which are separate from projects, but you can connect a project to a billing account if you want to have multiple projects charging the same credit card. This begins revealing the way that these are all designed as hierarchical structures for IT departments to be thinking about. And this is a very common pattern that we see in cloud computing. These things are designed for IT managers to feel very comfortable around. As scientific researchers, these are new and mostly irrelevant concepts for us. And they're mostly things we don't need to think about if we're, say, using the type of cloud provided by UK Biobank or provided by Neurohack. So a billing account creates a project. All these things exist within an optional organization. And we can access these things in many different ways. We can log into a web browser and go to azure.com and use that to create a virtual machine. There are Unix tools that let us open a terminal and create and manage virtual machines. They call those the CLI tools. And then there are software development kits. So you can actually write a Python script that inside of the script creates a VM, turns it on, puts stuff in it, does work, then turns the machine off and then deletes the machine. If you see things like the SkyPilot project coming out of UC Berkeley, that's an example of a tool that uses Python SDKs to manage your cloud infrastructure for you. Then there's also this thing called infrastructure as code, which are really custom programming languages for describing how your cloud looks. And we can talk more about that if you want, but ultimately, I think we're getting close to the end of our hour-and-a-half together. And so I just want to remind everyone to stay in touch. Here's my email address. The cloud can mean a lot of different things. Ultimately, what I encourage you to think about here is the fact that you have agency in how you acquire computation, because you can get little bits of it that are exactly what you need using these cloud platforms. You might be using a cloud platform by paying an organization like Neurohack or UK Biobank to access their Jupyter hub. Maybe you don't need any of these things, but it's useful for you to be able to talk to people asking you why you're not using the cloud, because you know the costs and trade-offs. So with that, please be in touch. Please come ask me questions. You know how much I like those. It's been a pleasure getting to talk to all of you again this year. So thank you for having me. And I hope that this was useful to you guys.